Hello, welcome back to Physics 2. And in this lecture and the coming lecture, we'll be talking about the second branch of optics, which is physical optics. In this first lecture, we will be talking about interference of light, which is one phenomenon within the field of physical optics. And the contents of this lecture, in the beginning, we will introduce some introductory session. Then we will talk about Huygens wave theory and Huygens principle. Then we will introduce the concept of interference and define interference. We will discuss the conditions for interference. We will talk about the coherence condition. Then we will describe Young's double-slit experiment and its results. We will see interference by thin films, and we will look into the interference pattern produced by thin wedges. And then we will see Newton's rings produced by interference effects. Finally, we will talk about Michelson Interferometer as an application for interference effects. And to begin with, we have to remember that a large number of phenomena such as interference and diffraction of light cannot be described by geometrical optics. And these phenomena are understood or describable. They can be described if we use the wave property of light. This concept of wave propagation of light can describe such phenomena. Interference as a concept is broadly due to the superposition of independent wave trains propagating in straight lines. And this superposition of independent wave trains result in variations in the intensity of light in space. So this effect is called interference. The independent wave trains that interfere with each other to produce this intensity variation in space should be coming from coherent sources, having fixed phase relationship to one another, as we will describe during this lecture. The other concept, which is diffraction, is not very different from the concept of interference, with the exception that we use the term diffraction for the description of waves spreading around an obstacle or spreading or flaring from through an aperture. The interference effects which are produced due to these obstacles or due to the passage of light through an aperture is termed diffraction. But otherwise, as far as physics is concerned, there is no difference in the two concepts. The interference leading to diffraction is thus due to the superposition of secondary wavelets that are originating at different points of the same wavefront, because we are talking about a wave that is bending around an obstacle, or a wave that is going through an aperture. So we're talking about the same wave front, actually, and the interference effects that are due to what we call diffraction could be viewed as interference or superposition of the different parts of the same wave front with each other. That is how we can interpret it. And now we have to touch on some historical background. And we mentioned that in Newton's time, there were two rival theories for the description of light. And one of these theories is the wave theory, which is led by Huygens in 1678. This is the wave theory. And this theory is the first one. The second theory is led by Newton, who did not believe in the wave theory, and he set up his model for the description of light as being a stream of corpuscles that is traveling in space, like particles traveling in space. And that is called the corpuscular theory, which is suggested by Newton. And actually, Newton did not believe in the wave theory of light because he failed to see or to observe diffraction of light, because that was the condition for light being waves. So although the wave theory is successful, but at that time Newton could not see the diffraction. That's what led him to believe in the corpuscular theory. And interference of light observed by the work of Thomas Young, the double-slit experiment by Thomas Young in 1802, these interference effects that Young has observed were in favor of Huygens' theory, actually. And however, a century later, around the turn of the 20th century, Einstein's work on photoelectric effect has provided evidence that light also has this corpuscular or particle nature. So with the work of Einstein and the previous work, which proved the wave nature of light, it was so clear by that time that light has both a dual nature of particle-like or wave-like. And now we have to discuss the Huygens wave theory, the Huygens principle, and this is a geometrical construction of the wavefront of light. It's considered waves with wavefronts. It's the mathematical construction or the geometrical construction of the wavefront at any time. If the position of the wavefront is known at a given time, then we can construct the wavefront at any later time according to Huygens' principle. This construction is as follows. All points on a wavefront, so this is a wavefront and these are points, different points on a wavefront. All points on a wavefront act as if they were point sources. And these point sources, they emit wavefronts, spherical waves, because they are point sources. And these spherical waves are called wavelets, spherical wavelets that are arising from these portions of the wavefront. So if we know the wavefront, the position of the wavefront at a certain time, the position of each wavelet is known at any later time from the distance it travels, which is simply the speed of light times the time interval. After that, we can construct all the wavelets that are emerging from a given point on the wavefront, and the new position of the wavefront is simply the tangent, the surface that is tangent to all of these secondary wavelets. So this is how we construct the new wavefront. Knowing the initial wavefront, we can construct the new wavefront at a given time, which is delta t, after a time delta t, using Huygens principle. And now we move to talk about this interference of light, which is the first topic within the physical optics that we are tackling. And we have to mention that it is a superposition of wave trains, of course, as we mentioned. And the superposition of, we consider the superposition of two waves having the same frequency and fixed phase difference phi at any given point in space. Let's remember that we should have these two waves, which are superposed. They have to have fixed phase relation at a given point in space. And if these two waves are of amplitudes A and A prime, then the electric field at a given point in space at a given time is simply the first electric field, which is A, the amplitude A, cosine omega t plus A prime times cosine omega t minus phi. And here we have to mention that the second wave lags behind the first wave by phase phi, and this phase is fixed in time, is constant at a given point in space. So, and we have to remember that the electromagnetic density, energy density, is proportional to E square. So we square the electric field here, and the square of the electric field is simply A square cosine square omega t plus A prime square cosine square omega t minus phi plus 2A prime cosine omega t minus phi. And here we expand this term, which is cosine omega t minus phi, because here we have cosine omega t and here we have cosine omega t minus phi. So if we expand it, we will end up with E square is equal to A square cosine square omega t plus A prime square cosine square omega t minus phi. We don't have to expand this because this is the only cosine term that exists there, plus 2A prime cosine square omega t cosine phi plus 2A prime cosine omega t sine omega t times sine phi. And now if we take the time average of this square electric field, the time average of the cosine square omega t is equal to 1/2. The time average of the cosine square of omega t minus phi is also 1/2. This also has cosine square omega t. The time average of it is 1/2. Now, the average of cosine phi is cosine phi, of course, because it's constant. It's assumed constant. And the average of A is A because it's constant. Now, the average of cosine phi is 0. And the average of sine phi, the average of cosine omega t, the time average of cosine omega t is 0. And the average of sine omega t is also 0. We can view this cosine omega t times sine omega t is an odd function in time. And the average of it is 0 in time. So when we take the average of the electric field, the square electric field, this last term drops out. It's 0. And we are left with E square average is equal to 1/2 times, in parentheses, A squared plus A prime square plus 2A prime cosine phi. And notice that this intensity or this electric field square, the average of the electric field, the value of it, which is proportional to the density of the electromagnetic energy, is dependent on phi, on the phase difference between the two waves. So for example, if phi is equal to 0 or 2 or 2 pi or 4 pi or whatever, 2 pi times a number, if that's true, then cosine phi is equal to 1, and then we will have A square plus A prime square plus 2A prime, which is the maximum, which is a plus a prime all square, the maximum value that's attainable. And if phi is equal to pi, for example, or 3 pi or 5 pi, then cosine phi is equal to -1. And then this gives the minimum value of E square. On the other hand, if phi is 90 degrees, for example, then this term is equal to 0. And we will have simply a square plus a prime square in parentheses. So this, the interference term is this term. This is due to interference, because if this term were not existing, then E square will be 1/2 a square plus a prime square, which is constant in time. But this is the interference effect, this term, which is 2a times a prime times cosine phi, which really depends on the phase difference between the two waves. And the conditions for the interference, as we mentioned a little while ago, is that for the constructive interference, we have a maximum value of the intensity of the electric field intensity square. The average value is maximum. That is when phi is equal to 2m pi. And we have a destructive interference when we have a minimum intensity when phi is equal to 2m plus 1 pi, which is 1 pi or 3 pi or 5 pi and so on, as we mentioned. So we have maximum intensity at this condition and minimum intensity at this condition. And the average, the time average of the quantity that we just took, the E square, when we average it, we said that the phase phi should be a constant, because otherwise, if phi is varying with time, then the average of the cosine phi will equal to 0 also. And we will not have this interference term, will drop out. So in order to have the interference effect that is observable, meaning having maximum at certain points and having minimum intensity at other points in space, in order to have that, we have to have this condition of constant phase difference between the two waves. It has to be assumed or imposed. And this condition leads to the concept of coherence of light. And we say that the condition for the interference is that phi is constant at a given point in space, which means that these two light sources or light waves, which bear this constant phi difference, phi phase difference, are said to be coherent. So we call these two sources which produce these two waves with constant phase difference between them. We call these sources coherent sources. Otherwise, the sources, if they don't bear the same constant phase between them, they are called incoherent, and the time average of the interference term of which contains cosine theta, the time average is 0, and then the electric field E is simply 1/2 times a square plus a prime square, which is constant all over space. There is no variation in the intensity in space if we have incoherent sources. And incoherent sources is like if we have one light bulb and another light bulb, they are producing light. These are incoherent lights, so we don't see interference effects coming from this. A light source consists of a very large number of atoms, and these atoms are radiating independently. The time duration which an atom radiates light is 10 to the minus 8 seconds. So an atom radiates light during a time interval of around 10 to the minus 8 seconds. That's the time scale for the radiation. And thus, the coherence length of the elementary train is simply the time it takes for the radiation of the wave train by the atom times the speed of light, so 10 to the minus 8 second times the speed of light, which is 3 times 10 to the 8 meters per second, and that gives 3 meters. So the wave train is coherent over a length of 3 meters. This is the coherence length, and thus any experiment that encounters coherence and that requires coherence in order to see interference effects, the whole instrument should not be larger than 3 meters, because otherwise after 3 meters you lose the coherence of the same wave train, but you need coherent sources in order to see or to observe the interference effects. So this is a requirement. 2 points on a wave front are 2 coherent sources of secondary wavelets, because the same wave has the same phase. So if we take 2 points like this on the same wave front, the phase difference between these two is coming from the path difference. So we consider the path difference, and the phase difference between these two rays coming from these 2 points is equal to omega t minus ks. That's the phase for the first ray reaching point P. That's the phase of the first ray at point P, and the second is omega t minus ks prime, and that is equal to the difference in phase is thus equals to k times delta s, where delta s is equal to s prime minus s. And we can see that this is true because simply k is equal to 2 pi over lambda. So we have ks is simply s over lambda, which means that we are transforming this path length in terms of number of wavelengths. So when we divide s over lambda, we get how many wavelengths do we have in this path, and we multiply it by 2 pi in order to convert each wavelength. Instead of looking at it as wavelength, we look at it in terms of radians, in terms of angle. So we convert this way. When we multiply ks, we convert the spatial distance in terms of phase, in terms of radians in phase. So the phase difference is 2 pi delta s over lambda. This is a relation, and the condition for interference, for constructive interference, is that phi is equal to 2m pi, which is the same as saying delta s is equal to 2m lambda over 2. This is for constructive interference. And for destructive interference, the condition for destructive interference is that we have phi is an odd number of pi, which is the same as saying delta s if the phase difference is arising from different optical path lengths traveled by the different rays. Then the phase difference is obtained by saying delta s is equal to 2m plus 1, which is an odd number of lambda over 2. So odd number of lambda over 2 would give destructive interference, because at a certain point one wave has a maximum and the other wave has a minimum, and we have a destructive interference. They cancel each other. And for constructive case, we have delta s is equal to an even number of lambda over 2. Even number of lambda over 2, which is either lambda or 2 lambda or 3 lambda and so on, which means at a given point in space, a maximum of the first wave is lying on the maximum of the second wave, so the intensity is increased. So this is constructive interference and destructive interference. And now we talk about Young's double slit experiment in interference. And this is a historically important experiment where initially interference effects were not observed because there was difficulty to obtain coherent sources. And what Young did is that he first of all obtained coherent sources as follows. First of all, he let the sunlight fall onto a very small slit. This very small slit picks a very small pencil of light which emerges from this slit as a single wave. So it's like almost like a wave that is a single wave train that is radiated by a single atom. It's something like that. So we are dealing, after the slit S, we are dealing with a single wave. And now, when this single wave, which has the same phase, when it falls on these two slits, S1 and S2, then each slit will transmit light as if it is a source of light. So slit number 1 will be radiating light as if it is a spherical, as if it is a point source, which gives spherical waves, and S2, the same thing, will give spherical waves. So these two spherical waves emitted by S1 and S2 will interfere, and they will have maximum intensity in certain directions, like this direction and like this direction, where they cross, and they produce maximum intensity, and they have minimum intensity in between, where the intensity is cancelled, and we see dark regions in between. So this is the principle of Young's double slit experiment. And in this case, if we look at the geometry of the experiment, we have the difference in optical path, which is delta S, is simply equals to d, which is the distance between the two slits, times sine theta, where this is sine theta. Theta is the angle that is made by the ray that makes up this point, and this line, the axis perpendicular to the line between the two slits. And the condition, if this delta S, this optical path difference, which is equal to d sine theta, if we set it as equal to an integer times lambda times the wavelength, then we have a constructive interference. And this defines the positions theta of the bright fringes, because we have constructive interference. So this condition is the condition that gives bright fringes. At these thetas defined by this relation, we have bright fringes, and if we set the relation phi is equal to kd sine theta, as we have derived a little while ago, because phi is equal to simply k times delta S, which is kd sine theta. This, if we put it back into the relation that gives the intensity, or the E square term, we will get the intensity distribution of light. So that way, we get the positions of the bright fringes, the position of the bright fringes where maximum intensity is observed, and by the other condition, phi is equal to kd sine theta, we get the intensity at any position theta, actually, in space. So we get the modulation of the intensity in space. And the intensity of light, if we assume that the two waves have the same amplitude as we have done by Young's double slit experiment, because we are dealing with the same wave and we are picking two slits, and if the two slits have exactly the same size, then the amplitude of the wavelets are the same, and A is equal to A prime, which we assume to be E naught, the amplitude of the wave. And in this case, E square average from the previous formula reduces to the shape E naught squared times 1 plus cosine phi. And this cosine phi is simply kd sine theta. That means if we set instead of the electric field square. If we put it in terms of intensity, then this reads I is equal to 2I naught times 1 plus cosine kd sine theta, and this relation defines the intensity. We can rewrite it in this form: I is equal to 4I naught times cosine squared of 1/2 kd sine theta. That's by manipulating the trigonometric function. And this intensity, if we normalize it to I naught, I over I naught will look like this. It's a cosine squared function. So if we plot this against sine theta, it's like cosine squared function, and this is the shape of the cosine squared. So we have maximum intensity of 4I naught at certain positions, where these positions are defined by the optical path difference being equal to an integer number of wavelengths, and then we have minima at positions defined by the fact that the optical path difference is equal to an odd number of half wavelengths. And now we consider the interference by thin films, as interference can be observed not only from sources like the two slits that was done by Young's experiment, but also interference can be observed between lights reflected from the upper face and the lower face of a film. So if we look at light being reflected from the top part and the bottom part of a film, these rays can interfere, and they can produce modulation of the intensity in space. And this can be seen by the fact that there will be a phase difference between these two rays, the rays that are reflected from the top face and the rays that are reflected from the bottom face, because simply there is an optical path difference that can translate into phase difference, and there's also reflection here, reflection from this interface, which is different than reflection from this interface, because this interface is reflection from a denser medium to a lighter medium, and here it's a reflection like from a lighter medium to a denser medium. So these two reflection processes are different. So we have two sources of the phase difference, and the two sources are, one of them is arising from the optical path difference, and here, because the two media have different indices of refraction, we look into the wavelengths in the two media. Lambda in the first medium is simply C over N over the frequency nu, which is lambda over N. In the second medium, the wavelength is simply C over N prime over the frequency, which is lambda over N prime. And now we calculate the optical path difference, and we divide it by the wavelength lambda and multiply by 2 pi. That means we multiply it by k in order to translate the optical path difference as length into an angle in radians. And the difference in optical path is equal to this length OC, but here OC we multiply it by n prime in order to account for the difference in wavelengths in this medium. And the second part is this part, which is CB, times n prime in order to convert the length into the right lengths of lambda prime here, minus this optical path, minus this path, which is OA in medium n, which is simply n times OA in terms of lambdas here. This gives the phase difference due to the optical path difference, and thus this reads like this: phi is equal to 2 pi over lambda times 2n prime OC plus 2n OC times sine theta prime, where here we converted OA in terms of OC and sine theta prime and sine theta by simple geometry. And we use Snell's law, where n sine theta is equal to n prime sine theta prime, so we will have n prime in both terms, and we will have 1 minus sine squared theta prime times OC. And if we consider that L, the thickness of the film, is equal to OC times cosine theta prime, and we remind ourselves that 1 minus sine squared theta prime is equal to cosine squared theta prime, putting these facts together, we will obtain phi is equal to 2 pi over lambda times 2n prime times L cosine theta prime. And now this is the phase, and the phase difference due to reflection at the boundary, we can calculate it from this principle, that from the principle of reversibility, it can be shown that the reflection at a boundary of denser medium introduces a phase difference of pi, which is half a wavelength. However, from the reflection at a boundary of a lighter medium does not introduce any phase difference. So introducing this additional phase difference from the upper face, because it is reflected at a denser medium, the total phase difference is simply 2 pi over lambda times 2n prime L cosine theta from the optical path difference minus pi, which is arising from the reflection. And now the conditions are such that phi is equal to 2m pi gives constructive interference, as we mentioned, and phi is equal to 2m minus 1 pi gives destructive interference. And if we put the value of phi and we move the pi to the other side of the equation, we have 2n prime L cosine theta prime is equal to 2m plus 1 lambda over 2 for constructive interference. And this quantity, which gives the thickness of the film, is equal to 2m. When it is equal to 2m times lambda over 2, an integer number of the wavelength, it gives destructive interference. And this gives the facility to measure the thickness from the interference pattern, to measure the thickness of the film, actually. And in normal incidence case, theta prime is equal to 0, in which case 2n prime L is equal to these values for constructive and destructive interference. And for a thin wedge, if we consider that alpha is very much smaller than 1 radian, very small, then this can be considered as a thin film, like what we have derived a little while ago. And if we call the thickness at a given point as T instead of L, then we get exactly the same result as we have obtained a little while ago. T, the thickness at a given point, is equal to 1 over 2n prime times 2m plus 1 lambda over 2 for the bright fringes. At this thickness, we get bright fringes. And at this thickness, which is given by T is equal to 1 over 2n prime times 2m lambda over 2, we get destructive interference and dark fringes. And that is why on the thin wedge, we see stripes of, if we have a longitudinal slit light, we see this pattern of stripes where we have dark and bright regions on the thin wedge. And here M runs from 0, 1, 2, 3, and so on. And at M equals 0, which is at the beginning of the wedge, we have a dark fringe. Newton's rings are also manifestation of this interference by thin films. And Newton's edge it's like a section of a spherical glass sphere, part of a glass sphere on top of another glass film, and the light is falling like this, and it is reflected from the spherical surface and from the bottom, and these reflected lights would suffer interference, would encounter interference, and they would show an interference pattern. And this device that produces the interference which is this wedge, it can be considered like a wedge of air, where n is equal to 1 at this, and we can get exactly the same result as for the thin wedge or the thin film. And in the case, if we have this small r is much smaller than the radius of curvature of this surface, in this case, we have the approximation t, the thickness of the air wedge, is equal to r times 1 minus cosine theta, and this is equal to 2r sine squared theta over 2, which is r squared over 2 capital R. And the interference pattern looks like this, where r squared, the same condition that we have obtained before, is equal to 2m plus 1 into r lambda over 2 gives bright fringes, and at a radius from the center of 2m r lambda over 2, that gives dark fringes. And m here runs 0, 1, 2, 3, and so on. And at this point, I would like to just mention quickly about the Michelson Interferometer. This is a device, Michelson Interferometer, devised in 1881 by Michelson. It's a device that can measure lengths or changes in lengths with great precision and accuracy. And here in the device, we don't have any phase difference introduced by reflection, because the same number of reflections occur in both rays, and just the motion of the mirror M2, the motion of it, will introduce an optical path difference of delta S is equal to 2t, and the phi, the phase difference, is simply 2t times 2 pi over lambda. We convert it into angular phase difference, and the conditions are as before. Phi is equal to 2m pi gives bright fringes, 2m plus 1 pi gives dark fringes, and the distances are measured by counting the number of fringes that appear to pass a given point in the interference pattern. And thus, if n fringes happen to be counted to move across a given point, then the distance t is equal to 1/2 n times lambda, because 2t is equal to n lambda. And this result can be used to measure the thickness L of a transparent dielectric film placed in front of M1. And this is given by t is equal to NL. At this point, I would like to finish my lecture, and thank you for your attention.